Ramanujan for G is now available on the Google Play Store. Try it out for free.
So, hi students. So today we continue with the the material. Last time we looked at transformers, and then we started looking at the idea of electromagnetics in the context of electromagnetic waves. And so today we will go back there. And then we'll go forward from there, Um, so here is what happened in the 19th century. Okay, lot of this happened in the 19th century. So first there was all these people who discovered various phenomena associated with electromagnetics. There was firstly the current side. There was Gauss law, then there was Ohm's law, then there was Ampere, and finally there was also Faraday, and then after all these things happened, there was Maxwell. What Maxwell did was he compiled all the different things they found. There was of course Tesla, um, but all these people, they kind of came a little bit before. So it was Maxwell who then compiled everything that happened in before him into four equations. Okay, so Maxwell's equations today are the basis of modern electromagnetics. We understand electromagnetics today largely through the four equations of Maxwell. There's no new stuff after Maxwell really in electromagnetics. There was maybe a little bit after that, but Maxwell's equations form the foundation of electromagnetics. Okay, and they form even today, all that, they are still very relevant even today. Okay, when we come to look to understand electromagnetics. So let's get started with that. So the first thing that happened after Ampere's law was the idea of displacement current. Okay, the displacement current was an addition to the conduction current, right? B dot dl equals mu 0 I. I is essentially conduction current. Okay? So then after the emergence of alternating current and everything that came with that, they then added a second term. That second term, B dot dl equals mu naught I. This was Maxwell's equation. So they added this term. Okay, this term is what we call as displacement current term. Okay, B dot dl equals mu naught I is true only after you introduce the the second term. Okay, and this second term is epsilon naught dou phi by dou t. Okay, epsilon naught dou phi by dou t is what we now call as displacement current. And where does that happen? So if there is a parallel plate capacitor in the circuit, now what happens in a parallel plate capacitor is there is not an actual flow of electrons, but there is still a current. Okay, and so how does that happen? Basically, there is a electrical flux that kind of produces a current, and that electrical flux is phi e, and the rate of change of electrical flux is then epsilon naught d phi by dt, then becomes another form of current, and that current is what we call epsilon naught d phi by dt is the displacement current that gets added to the equation. Okay, so now the other way is that they introduce this other term called H. Okay, H is, instead of B, they have H. Okay, and so H is typically when they quote Maxwell's equation, they use H. Okay. Now, but displacement current ID is epsilon naught d phi E by dt. And so the displacement current is epsilon naught dE by dt, JD, dE by dt, and so using that, you then have the displacement, or epsilon naught JD is the displacement current density. All right. So now B dot dl equals mu 0 I now has a second term, and so and that term comes from the parallel plate capacitor. So inside the parallel plate capacitor, if you do B dot dl, right, you then end up with, or you then add also this other term phi E equals pi r squared E. And what is E? E is the electric field, right? So, and E is E dot dl equals sigma by epsilon naught, right? So, and therefore from that you end up with the second equation, right? Sigma is what? Sigma is the current density, is the charge density, q by pi r squared. Okay, so now using that, you then end up with d phi by dt equals r square by epsilon naught square r square. So now, where did you last see phi E, right? Gauss's law, right? So Gauss's law states that the E dot dA, right? Gauss's law deals with E dot dA, right? Q by epsilon, right? Now, and so that is the idea behind this, that they add a second term to facilitate the displacement current. Okay. So we already looked at this side of it. B dot dl equals mu naught I, right? B and dl is what? dl is a line integral, right? Line integral over a circle 2 pi r, right? Therefore, that produces mu naught I, right? So the magnetic field is continuous at r equals r. Okay. Therefore, you end up with mu naught I by 2 pi r. Okay. So the highest point of the magnetic field is right there at r. Okay. Now the displacement current adds the second term, right? Therefore, you have B dot dl equals mu naught IC plus mu naught ID. ID is epsilon naught d phi E by dt. Okay. Therefore, you have to derive that displacement current, and that phi E is the based on the flux, the enclosed electric flux, and for that you have to use Gauss's law. Okay, so that is the basis of this whole discussion here. Okay, and so there you derive the displacement current. In certain cases there is no conduction current, and there is only a displacement current. Okay, and in those cases you end up with this kind of an equation: B dot dl equals, this goes to 0, and then you have mu epsilon naught d phi by dt. D phi by dt is essentially that. Okay, so there is a portion which over which you have the current flowing. Therefore, you have this mu naught r by 2 pi r square. Okay, that's B equals mu naught r by I by 2 pi r square. Okay. So so that's how this whole thing works. So a parallel plate capacitor is getting charged, and so this is a simple problem. The current at a specific time is 0.45 amperes. The radius of the plate is r equals 5 cm. Calculate the total displacement current. So for that, you have to enclose the space, right? And then you have to use calculate the displacement current density, right? So for that, you first have to calculate the displacement current using B dot dl equals mu naught epsilon naught d phi by dt, and then you have to include the phi, which is the electric flux. Calculate the displacement current density. So So when you have R less than R, you have B equals B dot dl, right, equals mu naught I, right? And if you have R greater than R, then you have then the current that is enclosed when R is less than R is a subset, right? So you have a current which is uh, R by R mu naught R by R I. When R is less than R, you have the current as being mu naught R by R times I. And then you have B dot dl is 2 pi R. Okay. So based on that, you end up with this. You are now in the straight line phase of that equation. You're now here. When R is less than R, you're now here. Okay. Now, when R is greater than R, then you have the full current, mu naught I, and therefore B dot dl equals mu naught I. Okay. So this is pre-Maxwell. Okay. And so now uh, the what happens to Ampere's law when there is no conduction current? Okay. If there's no conduction current, there's only a displacement current. So let's say you had a circuit, where there was only a capacitor and there was a displacement current due to, a changing magnetic field. Then this is what happens there, right? B dot dl equals mu naught epsilon naught d phi by dt. There is no mu naught IC. That term has disappeared. There is only this term. Okay. Now, Faraday's law also transforms to closed integral of E dot dl equals minus d phi by dt, right? This is the standard Faraday's law. There's no change there. Okay, but the B is derived from the corresponding equation here. So these are the two changes as a result of there being both a conduction current and a displacement current. All right. So now epsilon naught, right, is actually, it shouldn't be epsilon, but it should be epsilon. Okay. Epsilon is the permittivity of the medium. Okay. Now, when the permittivity of the medium, right, basically the JD, has this additional term which is based on the frequency of the current. Okay. So that frequency kind of changes the whole dynamic of this. Okay. So sometimes when your current density exceeds the omega, the frequency, current density is far greater than your omega epsilon, right? When your current density is far greater than omega epsilon, then you are largely looking at the behavior of the whole system as a conductor. While if the current density is much smaller than omega epsilon, then you're largely looking at the behavior of the dielectric and the displacement current. Okay. So Maxwell's equations were therefore transformed into a new set. Okay, this is Gauss's law. E dot dA equals Q enclosed by epsilon. Gauss's law. This is the non-existence of magnetic unipoles. B dot EA equals 0. Right? You will always have a north and a south pole for a magnet. Right? Then this one is E dot dl equals minus d phi by dt. This is Faraday's law. And then finally, Ampere's law has the second term, and these four equations became Maxwell's equations. Maxwell's equations normally, when they are quoted, are not quoted in this form with these closed integrals on one side. Okay, Maxwell's equations are usually written in this form: del dot E equals Q by epsilon, del dot B equals 0, del cross E equals minus B dot. Okay, del cross H equals mu naught I. Okay, and H is of course includes the displacement current. Or del cross B equals mu naught I plus mu naught epsilon naught d phi by dt. Okay, so that is how these Maxwell's equations are usually quoted. They are quoted as straightforward partial differential equations. Okay, but typically when in um, pre-undergraduate calculus, pre-undergraduate electromagnetics, they always close it, quote it using E dot dA equals Q by epsilon, B dot dA equals 0, E dot dl equals minus d phi by dt, and close it to B dot dl mu naught I plus mu naught epsilon naught d phi by dt. Okay, and therefore, therefore, those are the four equations. From Maxwell's equations, you can derive the speed of light. See, the speed of light is E naught by B naught, or 1 by the square root of mu naught epsilon naught. Okay, C equals 1 by the square root of mu naught epsilon naught. Notice that this equation has mu naught epsilon naught here. That is C. Okay, so, or 1 by that, 1 by square root of that is C. So that is actually 1 by C square. Okay, now you may remember this same equation from your wave equation, right? So your wave equation is what? Dou square V by dou square phi by dou x square equals 1 by C square dou by dou square by dou t square of psi, right? So that was the wave equation, right? Now electromagnetic is also a wave, so that's where we are going next. Okay, now when we looked at the sinusoidal wave, right, you had y of x comma t equals a sin x kx minus omega t, right? And you may remember this. We did this partly from the class 11 stuff, right? When we discussed waves. Therefore, we had the wave number 2 pi by lambda equals k, where k is the wave number, k equals 2 pi by lambda, lambda is the wavelength, and k is the wave number. Then we had also the omega, right? Therefore, and then we said the speed is omega by k, right? Omega by k. And so from that, right, we then derived, see this one, omega by k. Velocity, the speed was omega by k, right? Therefore, from that, we said omega by k, the 2 pi's cancel, and therefore we have f lambda, right? The velocity equals f lambda, c equals f lambda, right? Therefore, and so that same wave equation is what you see, which we saw in the context of strings, we saw in the context of sound, which is a longitudinal wave. We also see in the context of electromagnetic waves. Electromagnetic waves are transverse waves, okay, and they can propagate in free space. Okay, the electromagnetic field, the electric field and the magnetic field are perpendicular to each other, and they are both perpendicular to the direction of the propagation of the wave. Okay, so if this is x, this is y. Okay, E and B are perpendicular to each other, and they are both perpendicular to the direction of the transmission of the wave. The direction of the transmission of the wave is in the direction of E cross B. E cross B will give you the direction of the propagation of the wave. Okay. Now, we of course know that there are bundles of waves, but right now we are not dealing with that. Now talking of one wave. And in one wave, the E is a wave, right? And the E, let's say the E was in one direction, the B will be in a perpendicular direction, and the E cross B will be the direction of the propagation of the wave. So here, if E is I E sine kz minus omega t, and B is J B naught sine kz minus omega t, they both have, notice that they both have the same wavelength and frequency, right? And therefore, because they are entirely completely connected, then you have the third direction, E of E cross B, being the direction of the propagation of the wave. So if the E is along X, the B is along Y, then the direction of propagation of the wave is along Z, along or E cross B, along the direction of E cross B. Okay. So now when we talk of the electromagnetic spectrum, we have all these waves. You don't never have one wave, right? In the light spectrum, we have so many waves. We have radio waves, microwaves, infrared, the visible spectrum, ultraviolet, X-rays, and gamma rays. Okay, radio waves and microwaves are below infrared, X-rays and gamma rays are above infrared. Ultraviolet, X-rays, gamma rays are above the blue. Okay, the visible spectrum is just 4 to 10, 4 to 7. Okay, visible spectrum is 4 to 7. Everything above is ultraviolet, X-ray, and gamma ray. Everything below is radio waves and microwaves. Okay, lot of the wireless happens in here. Here, and these are X-rays and all that. They are harmful. Wireless does not happen in this side of the spectrum. A lot of the wireless happens here. Then there is the infrared, which kind of heats, causes heat. Then you have these other things. Okay, so E cross B is the direction of propagation along the z-axis. So the wave propagates along the z-axis. Okay, so in free space, E dot dA equals 0. B dot dA is anyway 0 regardless, right? So now there are only these two that matter. And finally, using these two, we calculate E, and then B, then we take the cross product of the two. Okay. So now Faraday's law, E dot dl equals minus d by dt of B dot dA. Okay. Therefore, if E is I E sine kz minus omega t, E dot dl equals this one. Now, therefore, Faraday's law for EM waves df by dx, right, and therefore you can rewrite this E of z plus delta z minus E of dz by delta z equals dE by dz. Therefore, you can cross multiply that and produce this one. Okay, so now, and this you can do the same thing for the B as well. So when you equate that, you will find that dE by dz equals minus dV by dt. dE by z equals minus dE by dt. Therefore, from that, you have this equation. Okay, this equation is what leads to eventually this equation. This equation is what you see here. This equation is same as this way. E by B naught equals omega by K. Omega by K is C. Okay, so and therefore these derive basically from the retargeting of basically Ampere's law and Faraday's law. This is Ampere's law when there is no conduction current. This is Faraday's law. Okay, so when you have a combination of Ampere's law and Faraday's law, you then have this equation: E by B naught equals 1 by E by B naught equals C, which is 1 by square root of epsilon naught omega naught. Okay, so the speed of light is 3 into 10 to the power of 8 meters per second, and is the same as 1 by square root of epsilon naught omega naught, and it's also mu lambda. Okay, so for any particular wave, the mu and the lambda will change, but they will all move at the same speed, which is the speed of light. Okay, they may have a different wavelength and a different frequency, but they will have the same speed of light. Okay, so so what is the energy in an electromagnetic wave? The energy in an electromagnetic wave is half 1 by 2 epsilon naught E square, and which is and the magnetic side is 1 by 2 mu naught B square. So that is the energy in a electromagnetic wave. Okay, so so the total energy is the sum UE plus UB. Therefore, you have epsilon naught E naught square sine square K Z by omega T. Half the energy is in UB, half the energy is in UE. Okay, so and the corresponding average energy crossing unit area per unit time is U times C times so, and that is half C epsilon naught E square, and which is the intensity. The intensity is 1 by 2 C epsilon naught E square. Okay, so this is U, and you multiply that by C. Okay, so 1 by half epsilon C epsilon naught E square. Okay, so that is the basic idea. Okay, so so here is an example that that they have in the lecture in the involving with the IIT PAL lecture. So B naught equals F naught by C, right? E naught by B naught equals C, right? Therefore, they were discussing this Voyager 1, which was sent in 1977. It basically it was transmitting with a power of 20 watts. The antenna had a gain, and the receiver intensity was given by this I by, so E naught equals 2I by C epsilon naught using this formula. E naught equals 2I by C epsilon naught using this formula. Okay, to the power of half, right? So then you can then get the B naught using E naught by B naught equals C. Okay, so so this is the average energy, right? If you give the intensity, this is the average energy. Okay, so remember, so this is the same thing. Intensity is the power per unit area, and the same thing in the case of a laser. If they had, this is the power of the laser, and the radius is 1 meter. Power per unit area is the intensity. So from that you get the intensity, and then from that 2I by so you already calculated I, so 2I by C epsilon naught to the power of half will give you the E, and Therefore, from that you can always calculate the B. E by B naught for any electromagnetic wave is C. Therefore, from that you can calculate the E by B naught. So that is as far as the material that we have with respect to electromagnetics. What I recommend students do at this point is that see, electromagnetics as understood with respect to the wave side of it is involves partly this and partly what you learned in the standard wave theory, which is which we dealt with in the context of class 11. So you have the standard wave theory omega by k, c equals omega by k, and then the corresponding sine kx minus omega t kind of derivations, and then the generalized wave equation. Let me quickly bring the wave equation also up for you. And so this was pretty much what came out of the the Maxwell side of things. Let me in case you missed the wave equation. This one, okay, one dimensional generalized wave equation dou square f by dou x square equals 1 by mu square dou square f by dou t square, right? And so this equation also applies to electromagnetic waves. Okay, this is the generalized wave equation, also applies to electromagnetic waves. So now instead of 1 by v square, you have 1 by mu naught epsilon naught. Okay, so so I wanted to make sure that you saw this equation and you were able to connect the dots between what we did with respect to generalized wave equations and what we do with respect to electromagnetics. Okay, so this is as far as electromagnetic waves are concerned. Now, we will be continuing the discussion with respect to light in the context of the class 11 material. As of now, we will continue with more optical instruments and then move on from there. Okay, now with respect to the class 12 material, we will be next looking at the next set of ideas which deal with the photoelectric effect. Okay, the photoelectric effect will then provide a segue into what happened after. The photoelectric effect was what got Einstein his Nobel Prize. Okay, Einstein did not get a Nobel Prize for either of his relativity theories. He did get a Nobel Prize for the photoelectric effect. So we will be discussing the photoelectric effect and then hop into modern physics from there. Okay, then we will look at wave particle duality, and then we will look at the idea of the Bohr atom, and then the corresponding other work. First the Rutherford, Thomson Rutherford experiment, the Bohr atom, and then we will go on to the modern physics in the context of the nucleus, and what happened with the various particles that were discovered and everything else that resulted in the years after. Okay, and then maybe a little bit about quantum theory as well. Quantum theory typically in the context of class 12, a lot more quantum theory is actually taught with the modern physics that you learn in chemistry. You'll do a lot of that material in chemistry, and therefore I highly recommend that you attend Professor Tiwariji's classes as well, where you have a lot more of the material dealing with in the context of chemistry. Okay, so but then this material we will continue. We will look at from a physicist point of view. We will look at modern physics next, starting with photoelectric effect, etc. Okay, so so But then, see, I don't want to get started with the photoelectric effect today, so I will be starting the photoelectric effect starting next class. Okay, and this material is a quite non-intuitive. Everything about electromagnetics to me was non-intuitive. This material is even less intuitive. Okay, how do how does how at the lowest level, how does matter behave? How subatomic particle physics is extremely non-intuitive. You know, it of course comes from what we learned in electromagnetics and what we learned, but then there is a lot more that happens there. There is weak weak interactions, and there is also very strong interactions which happens in the context of nuclear physics, right? Nuclear physics is what happens in the nucleus of an atom, right? There's a lot that happens in that context as well. Some of it is explained by quantum theory, and some of it is explained by what we see in involving standard electromagnetics. So with that, I'm going to stop. So electromagnetics will continue. We will look little bit again at Lorentz. The Lorentz force, EQ plus Q times V cross B. Then we will also then look at because that is what happened. That is what got started with the Thomson experiment, and then we will go from there on to the Rutherford model, etc. In re-engaging with all the material that we learn in modern physics. So much of it is so relevant to all the things that we use in daily life. Just as electromagnetics is so relevant to daily life because of the use of electricity, modern physics also today is very relevant in all the things that happens, in all the semiconductors, etc. And there's so much to it that you wouldn't believe that that you cannot learn enough of it in the context of what you learn in high school physics. But yet we try to do what justice we can with this material. So with that, I'm going to stop for today, and we'll again engage next class. So till then, be safe and have a wonderful week ahead of you. But we'll re-engage starting with the photoelectric effects with the next class. Thank you.